Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we'll be looking at GCSE chemistry, exothermic and endothermic reactions, and we will continue from our yesterday's video. So yesterday we sort of covered the basics of exothermic and endothermic reactions. So make sure, if you don't know much about these reactions, what they are, the basics of how they work, make sure you check that video out. I will include it in a link in the description below, so make sure you give that a look. And today we'll be all about reaction profiles, how these reactions look on a graph. So, without further ado, let's get started. There we go. So, what is happening in both of these reactions? So I will remind you that exothermic reaction is when the energy stored in the reactants is greater than energy stored in the products, and therefore in a process of reaction we need to release that energy, we need to transfer that energy to the surroundings. Whereas in endothermic reaction the opposite is true. We have reactants which have less energy stored in themselves, in their bonds, as opposed to products where there is more energy stored, and therefore we need to add energy from surroundings, guys, to the reaction in order to make it work. So let's start with exothermic and let's see what the graph looks like. So here's the reaction profile graph for a typical exothermic reaction. So first of all, in y-axis we have energy stored in the molecules, be they reactants or products. Whereas in x-axis here horizontally we have a reaction progress, so simply the time, the way the reaction progresses. So let's see what's happening here. So this line represents the energy level of reactants, and this line here represents the energy levels of products. And we can see that reactants are quite high here because they have quite a lot of energy stored, and products are very low because they don't have much energy stored in a typical exothermic reaction. And then here in the red line we have the energy change. We have the line that shows how energy changes throughout the reaction. Now, what is happening here? So here we can see how the line, overall the line goes down. Overall the line goes down. And the distance here between reactants here, that distance there, this is the overall energy change. So I'm going to write this down. Overall energy change. So we have energy stored in reactants and we have energy stored in products. And that energy goes down from reactants to products. And the energy between reactants and between products, all this energy here, that's the overall energy change. This is basically the energy that we need to transfer away to surroundings. We need to transfer away to surroundings all of this, guys. Now, as you can see, the line doesn't quite look like this. I mean, if this was the case, that we are just getting rid of this overall energy change, if that was the case, then this line would go somewhat like this. Simply there and then drop straight down to products, right? Because that's what we're losing. However, what we are actually seeing when we look at these graphs is that we have this red line, and the line goes up first before dropping. What is happening here? Now, this is due to something called activation energy, guys. Now, what is activation energy? Activation energy is a little bit of energy that we need to supply before the reaction starts. Why? Because let's think about how reaction starts. Reaction starts with molecules or atoms colliding together. They collide together with a required force to trigger the reaction, to stick together or whatever they're gonna do to trigger the reaction. So we are supplying here we need to supply that energy to those molecules in order to allow them to collide in the first place. So first we need to supply some of that energy, we need to supply some extra energy, which then gets transferred away to surroundings anyways. But it is necessary to start the reaction to get those molecules colliding with force that is required of them to basically trigger the reaction, guys. Now, what's going on here? We have reactant, we have product, and why is this useful? This is actually pretty useful to us, because this is what prevents spontaneous reactions. Imagine if, say, we had matches, and matches undergo combustion. We strike the match, and it starts burning, and it combusts. Now, if we are supplying that activation energy by striking that match, by scraping it against the side of a matchbox. Now, what is happening here is we are providing friction, which in turn provides heat. And that heat, usually we will provide activation energy using heat. And that heat is what triggers the reaction. Now, imagine if we didn't have that. Imagine if we didn't require that activation energy, then simply those matchsticks would spontaneously combust. And also on a bigger scale, the world would have much less atoms, and we wouldn't be able to harness these reactions in the way we want them, because anything that would have a favorable energy change, anything that would have result in a release of energy, essentially would just spontaneously react and would leave us only with endothermic reactions. So we would actually have much less reactions to work with. So the fact that we have that activation energy is useful. And of course, this is a typical exothermic reactions, and things can change, things can look different. For example, in some reactions we may need a lot of activation energy, even though that reaction can still be exothermic at the end of the day. Likewise, reactions can be more or less exothermic. We can have much bigger drops or much smaller drops. Each reaction may differ, and reactions can progress at different speed. They can progress faster or they can progress slower. And all these information are contained in these graphs, which is why they are, guys, so useful. Now, let's have a look at what happens in endothermic reactions. So here we have a typical graph for an endothermic reaction. Again, energy in y-axis, reaction progress in x-axis, and reactants here, products here. Now, reactants here start with a very low energy store. They don't have much energy stored because it's an endothermic reaction, whereas products have much more energy stored. So here it is quite clear that we need to add energy from surroundings. Again, this usually will be by heat. Usually we will just simply heat up the surroundings of the reaction and thus provide that required energy. But let's see what's happening here. So again, we need to provide energy, and once we provide that energy, reactants become products. So the energy change goes somewhat like this. And again, overall energy change will be between those two lines, like this. And I will write that down again. Overall energy change. Sorry guys. Change there. So overall energy change is between those two lines, but again, we are noticing that we do not have this. The line goes like so. It doesn't go straight to the product. It goes in this arc. And again, this is due to activation energy. Now, the important thing to consider though here is that in exothermic reaction, the activation energy is just the difference between the peak and reactants. Now, this is actually the same in endothermic reaction. The activation energy is a difference between the peak and reactants. But this may look confusing. Why is the whole arc basically activation energy rather than just this part of arc between products and peak? Well, let's think back to what activation energy is. Activation energy is the energy required to start the reaction to get those molecules colliding with a required force. So in exothermic reaction, overall, we were releasing energy, whereas here we need to supply energy. So basically, in order for the reaction to even begin, we need to supply all this energy to cover the overall energy change. So we need to supply all of this energy, and then on top of that, we need to supply a little bit of extra energy to give those molecules enough of a collision force. Now, so that's why that activation energy is so big, and that's why it goes from reactants all the way to the peak, because we need to cover basically the whole overall energy change, and then on top of that, we need to cover the little bit of energy here to provide molecules with collision force. Now, this explains why endothermic reactions often require such high temperatures, because the activation energy is simply so high. It is simply so high. Exothermic reactions tend to have lower activation energies. You know, there are exceptions, but they do tend to have lower activation energies compared to endothermic reactions, which you pretty much have to do in a furnace or a kiln. So, these are the reaction profiles when we look at the energy changes in the reactions. And this is it for today, guys. Next time we'll be covering more mathsy side of it, I suppose. We'll be looking at the bond energies, and we'll be looking at how we can actually calculate these energy changes quantitatively. So, thank you very much for watching, guys. I really appreciate when you guys watch my videos. And if you have any questions, shoot me a question in comments. I'm more than happy to answer. I really like answering your questions, guys. So, if you want to stay up to date on daily math, science, and some biomedical science videos, hit the subscribe button below. Don't be shy. Thank you again for watching, guys, and see you next time.